Welcome back, everybody, to part 3 of this Clinton Marshall radio. We really don't know what year, somewhere around 35, 36, I think. But I guess the first question you're going to ask is, where have you been? Well, I really haven't been anywhere. I've just got sidetracked in some other things. I've been well. Everything's been going, I guess, the way I've been wanting it to. I've just got interested in some other things. I'll shoot a small clip of some of the radio equipment that I've been working on and have put on the air. I've put on an AM station, not a commercial radio station, but an amateur radio station, comprised of a Hallicrafter's HT37, which started out as a parts rig that I ended up repairing and putting on the air, and I get on it several times a week. And then I've just recently redid a Hammarlund HQ129X receiver from the late 1940s that I've added to that AM station, and it seems to be working great, and I'm having a lot of fun with AM on the ham bands. And that's pretty much where I am. But as you can see, I have kind of done some disassembly and some mapping and drawing the schematics, trying to figure out exactly how to put it back together, and we're going to go there. So first off, I want to apologize for being gone, one thing, but the other is for the first two episodes in this series. You know, staying out of it for a few months, I have to go back and look at my videos to see where I'm at on it. And I realized that I ran around and around and around in circles avoiding things. So I apologize for that. Let's see what we're going to do. We're going to start working on this cabinet. One thing. We're going to do some gluing, basic stuff, gluing it back together. And I don't know how much of that I'll show you. I might show some, but yeah, I'm going to glue it back together, and we're going to clean up the cabinet. I'm going to try to find some Gojo, though without the grit in it, and try to use it on that and see if we can clean it up. Then we're going to clean this chassis and finish drawing up the schematic and identifying all the parts and where it all goes. And then last but not least, I promised in that last video that we were going to show the math and show, and it won't go into a lot of detail, but I'll show you the formulas I used. And I'll have to admit, I borrowed these formulas off of a web page, and I will give you the web page that the calculations for that capacitor or the value of that capacitor came from. And so that's you know, we won't go into a whole lot of detail because I personally don't understand enough to explain it to where I can make you understand it. But we'll see where we get to on that one also. And one of the things I want to give kudos out to Bill Renfro 9798 that pointed out to me that when we were looking at the fusing and putting the polarized plug and cord on this radio, in my mind I was going to go back the way it was originally done, where the neutral cord or the ground, the chassis ground, went through the on-off switch. And he pointed out that it would be better, and he really didn't say I was wrong, but he asked me why we wanted to do that, and he was real nice about it, and I appreciate that. But it's a point well taken. In this situation, you had a 50-50 chance of getting the neutral wire on the chassis. 50-50. In this case, with a polarized plug, we're going to be 100% sure we've got that on the chassis. So we want to redesign or reconfigure it to where that we are going to fuse the hot line and switch the hot line, and the neutral will go to the chassis all the time. So without further ado, let's go ahead and get started with some of this stuff. In order to clean this mess up, what I did is I took these two screws out. I took the little screw on that trunnion there, and there's a little eyelet there that this went in, which control the dial. So I labeled all the wires, and I lifted this out, so that'll give me more space. I can get this off, so I can clean this chassis up and then map more of this underneath here. And we're, I think, essentially going to have to basically rebuild this. Most of the parts are going to have to be replaced. So let's get it all cleaned up, and then we can go from there. Let's see if we can get this tuning condenser off. The wire's already been taken off. Looks like there's two nuts on the bottom with some sort of, I don't know if that's washers or grommets on there. And there, all there is sorry, I'm in your way, but let's see, star washers on this side and nothing on this side. So there we go, we've got that out. We can get that cleaned up. We can check that for shorts, but get that cleaned up for sure. And see, that gives us a whole lot to work with. Not really sure about this. If you'll remember this long capacitor that was in here that fell out, I believe it was a replacement for this one here. I'm thinking about taking this off. Looks like two screws. Take it off and find a place that put a couple of more capacitors underneath the chassis. May try to clean that up a little bit and put it back just for instead of leaving a hole there, but at least leave it there to where anybody in the future will know what it was intended for. Take a look at that chassis. I've gotten this out. It's got some writing on it. I can probably figure out what it is, but I think I'm just going to clean it up and spray paint it silver and maybe glue the top a little bit and put it back in just to plug that hole and for the legacy of the part that was in there. But starting over. Here's one of the projects that I've had. This is a late 1940s Hammerlin HQ129 communications receiver. I think this one weighs 47 pounds. And I'll let you look inside of it. Look at that regulator tube. Glowing. Nice purple. And I use this on AM, 80 meter, 75 meter AM. And this is the transmitter. This is an 80-pound 1960 Hallicrafters HT37. So getting ready for the net coming up. The band's still not hardly dark yet, so the band still kind of unsettled. Okay, did a little cleanup on it. Actually took and put it in a sink with some soap and a brush. Cleaned it up, and then took a little Brasso to just kind of polish it up a little bit. I think that's about all I'm going to do to this. Okay, we're going to go back to the Sky Coral whiteboard and just give a brief overview of what we're looking at doing here, just to make sure, recap this. We're going to go with a polarized plug, and so the neutral wire will always be connected to chassis ground. The other one, the hot wire, will go through a fuse, through the switch. It will branch off at that point to the B plus voltage to go to the plates and various other parts of the circuit to supply the high voltage. Now the heater chain, at this point where this is where we're going to insert a capacitor. Okay. Now, why did we choose a capacitor? Number one, the resistive line cord, it'd be harder to find one, and it's not the best application. A resistor, a power resistor, there's not that much room on the chassis to mount it, and just think of the heat it would have to dissipate, and it would make the chassis really hot. So we've decided to go with a capacitor. Now the capacitor doesn't generate any heat, should drop enough voltage, and the important key to this whole deal is from this point here to here, we will determine the voltage needed, and that we cannot let it get above that, because the last thing you want to do is destroy these heaters. Okay, now the first in the chain is going to be a parallel circuit of a 50 ohm resistor and two number 40 bulbs. The bulbs pull 150 milliamps apiece, and if you look at the heater chain, each one of these tubes pull 0.3 amps or 300 milliamps. So these only pull 150 milliamps, so the other 150 milliamps will be going through this resistor. Okay, we'll have to make sure the resistor's large enough and can dissipate the power. If one of the bulbs were to burn out, then the 300 milliamps would go all the way through this resistor, not burn the resistor up, but keep this heater chain going, so the radio still continues even though you lose a dial lamp. And I think that's important, or not, but the important thing is from this point to over here, and we will be monitoring it when we bring it up to make sure that we don't exceed whatever voltage we determine that, and we'll add that up here after a while. All right, the capacitor. Now this is a disclaimer right off the bat. I've had some school in electronics, but I am not an electrical engineer, and this explanation is a brief and a simplified one, so it's not intended to go really deep into the theory of capacitive reactance and what's happening and what's not happening and everything like that. All right, let's see if we can briefly and simply explain what's going on. A capacitor, you should know, and if you don't, this is basically what it does. It consists of two or more plates, and it's separated by a dielectric, and that dielectric can be air. Okay, what happens is when you apply voltage to the capacitor, current begins to flow. And based upon the polarity of that current, the dielectric, the molecules in the dielectric, they will polarize, and the electrons will collect at one plate, and the positive charges be at the other plate. Okay. Now, when you're using it in an AC circuit, and this represents, I'm sorry, this is not to scale or symmetrical or exactly, but anyway, this is a cycle, and as you probably know that this happens 60 times in 1 second in the wall circuit, 60 cycles. Okay, that means that the voltage rises positive, then it comes back to zero, then it goes to negative, and then it comes back to zero, and that's one cycle. Okay, well, during this phase, or this half of the cycle, the capacitor will charge in one direction and will store that energy. Okay, when it drops back down, then the power source, the polarity of it reverses. But it also, at the same time, the capacitor starts to discharge, which will be opposing to this. So it's going to be 90 degrees out. The current will be 90 degrees out of the voltage. So that means that when it crosses over, the capacitor will start discharging while this is trying to charge it in the other direction. So it's kind of, if you think about it, it's kind of like two waves hitting each other. They're going to cancel some of them out. And the amount of that cancellation is the capacitive reactance. And we're going to utilize that to get a voltage drop in this part of the circuit up here to protect this part of the circuit. And we will calculate that now. Let's take a look at some voltages here. This will be 6.3 volts, 6.3 volts, 25 volts, and 25 volts. 25 is 50. That is a total of 62.6 volts from here to here. Okay, so let's take a look at this. Now, let's make some assumptions here. Where did I come up with 100 or for 50 ohms? Well, some of the schematics showed 51 ohms resistor there. So that's where I got that. So we're going to work with that and see. Now, if we put two number 40 bulbs in series, we're going to make the assumption it's 12.6 volts. Okay? It's probably not going to be that, but let's determine the hot resistance of that bulb. And if we divide that by 0.15 amps, let's see, and I think 12.6 divided by 0.15, I think that's going to equal 84 ohms. Okay, so if we've got 84 ohms in parallel with 50, so we take and two resistors in parallel would be 84 times 50 divided by 84 plus 50, product over sum. So that'll be 4,200 divided by 134. That sound right? Let's do the math. And that's going to be equivalent to approximately 31 ohms. Okay, so let's figure the voltage drop across 31 ohms at 0.3 amps. So you got maybe you can see 0.3 amps times 31 is going to equal to our voltage drop. Let's see, 31 times 0.3 equals 9.3 volts. So we're going to call that 9.3 volts across there. And we'll see. We can make some adjustments if once we get there, it's not going to work. If you see anything wrong with this, let me know in the comments. And I'm just making this up as I go. Okay, we determined that this is 62.6. And this across here is going to be 9.3. And that's going to equal to 71.9 or about 72. Because we're going to say from here to here is 72 volts. So let's calculate from here. Okay, let's do these calculations. And then we'll put them in practice and see how they work. Nothing magic here. A couple of reference articles that I used. This is off of Nostalgia Air. Anyone's familiar with refurbishing these radios has used Nostalgia Air for schematics, but they've got a lot of resources, a lot of information on that website, and it describes about the line cord and the voltages and things like that. And it talks about, you know, that's the important voltages you want to make sure that you stay within. And what capacitors to use, etc., etc. The calculation that I used is from, and I print out a lot of my stuff because sometimes I forget where it's at, and I like a hard copy to read. I probably kill paper, kill trees, what have you. But anyway, it's Radio Ether, Restoring, Repairing Antique Tube Radios, and this article is from February 27th, 2008, and it shows the same typical circuit, and it talks about the different methods of calculating it, and on the back it talks about each step, how to calculate it. Okay, so the first step, it says, is to determine the current of the tube, and we've determined that the tubes are 0.3 amps, and then we summed up the voltage of the light lamps and the tubes, and we determined that it was 72 volts or so. So the next step is you determine the dissipation voltage, and this is the one that gets confusing, and they say trust him on this calculation. But this calculation for the dissipation voltage, and that's for the capacitor itself, is the square root of the line voltage, and I used 120. I guess I'm supposed to use a pointer, aren't I? Anyway, used 120 for the line voltage, and that number is squared, and you subtract your chain voltage squared. Okay, and when you do all that and you do the square root of all that, you end up with 96 volts. Okay, now the next step, it talks about you determine the effective resistance of that particular capacitor, and that's 96 volts divided by 0.3 amps, and that's around 320 ohms. Now the formula for determining the capacitor, or the value of the capacitor using these parameters, is the reciprocal of 2 times pi times the frequency times the resistance. We've done determine the frequency. Of course, 2 times pi is 6.28. The frequency is 60 hertz, and the resistance is 320. So we do the calculation, it ends up 120,576. We find the reciprocal, or divide it into 1, and it's 0.00000829, or if you move the decimal point over, 8.3 microfarads. So that's what we're starting with. Let me show you what I've got. Okay, doesn't that chassis look a lot better? Anyway, I bought this off of Amazon, and I used, I went and got the 250 volts because that's the highest rating they had, and you want to get the higher voltage rating in this application because of the way it's being used. And this is an 8 microfarad, plus or minus 5% or so. Okay, so I'm going to try that initially. Okay, and if it's not enough, then we will go, and here is, I got another one, and this is there's 2 in here. I can either go with a 2 microfarad or a 1 microfarad and couple it with this, and either have 9 or 10 microfarads for the capacitance. So I think, you know, I really don't have a problem with the chain being, the voltage being a little low on it. I just don't want it to be high. So we can adjust it with this, I believe. So that's how that's going to work, and that's the calculations. And the big thing is, I think about everything in there is going to have to be replaced. Of course, this looks like a big resistor, and we'll look at the size of these resistors and compare them to a modern resistor, because the old dog bones, they're a lot larger than modern resistors, and of course, like I say, the modern resistors, they'll dissipate a lot more for the size, so it'll look a lot different when we start redoing and rewiring all this. It's pretty much all going to be rewired, and I felt like that we could probably take that right there and mount the capacitor right there. I don't know if we could mount it underneath or not. That would probably be best if I could, but I don't know. We'll look at that. Maybe we'll mount it like that. All right. Let's get to reworking all this stuff. Okay. This thing's running on pretty long. I was going to try to include some of the cabinet work in this one, but it's a little long, so I'm going to go ahead and close it for now. As you can see, I've pulled a PTO, or a permeability tuned oscillator, out of a Collins receiver, and that's on the bench to be reworked, and I'll be working it in parallel with this. But when we come back, we'll do a little bit more cabinet, and then we will start repairing all this, replacing all this, and putting it all back together. Then we'll probably, in the next video other than that, we'll start powering it up and checking the voltages. So we've got a couple more in the series to go. So I appreciate y'all being patient with me, waiting so long for this installment, but we're eventually going to get through all this. So, from Larry from the hills of Tennessee, thanks for watching.